You pay attention with so much at stake.
Seas are rising and chronic flooding will be the new normal.
You navigate, you listen, you keep an ear out. You pay attention, and so do we. We tell the stories of our time every day.
In the 26th day of testimony and on the 139th witness, Shahar Tsarnaev wept.
We unearth what would otherwise stay hidden.
There's just a lot of hate in this world, and that day, for that hour, we were humans.
Across the street.
The Red Sox have won the World Series.
And around the globe.
It's here and now.
This is modern love.
This is WBUR's All Things Considered.
This is only a game.
This is On Point.
This is Radio Boston.
On air, online, on demand, and on stage in the heart of Boston.
I'm Jack Lepiars. Welcome to WBUR City Space.
Always looking forward, paying attention, and knowing that your story is one of our stories.
Good morning. I'm Bob Epps.
I'm Lisa Mullins.
I'm Meghna Chakrabarti.
I'm Jeremy Hobson.
This is 90.9 WBUR Boston.
Welcome. How many people, this is your first time here? A lot of you. So welcome. My name's Amy McDonald. I'm the Director of Community Engagement at BUR, but my main task is to program this space, and it's killing me. Go to www.wbur/cityspace. I like to call this the 92nd Street Y of Boston. We're doing everything. We're doing policy discussions, interviews with authors, the Moth Story Slam, live podcasts, cooking, music, dance, and opera. There's something for everyone, and it's such a beautiful space, isn't it? What we hear inside as well, you hear outside. So when people are walking by, they suddenly look and they hear something, or they see this beautiful LED screen and they sit and they join the conversations. It's such a streetscape. It's such a democratic part of Boston's home for civic conversation. So this is our third of our Boston Brilliance series. It was the brainchild of Khari Goldberg, our host of CommonHealth. And tonight we're going to hear from Eric Lander, brilliant Eric Lander, definitely fits the series title. A note about the Q&A. If you go to your phones, slido.com, you can type in your questions during the conversation. The password is EL610. I believe it will show up on the slide when you see it. And then you'll see your questions on the screen at the end. Oh, there it is. Oh, wrong, BB. Boston Brilliance, BB610, so you can just do that. Please welcome Khari and Eric Lander.
Ooh, okay, here we go. All right, hello, and thank you all for coming to Boston Brilliance tonight. I think this will be a treat. For those of you guys who have been here before, welcome back. And for those of you guys who, this is your first time, as Amy mentioned, what took you so long? I mean, come on. But no, really, thank you all very much for coming out. This should be really fun. First, I want to go back really quickly before we get started to the year 1990, a great year for the world. I showed up then. I was kicking around for, the most of it, but I showed up eventually. But okay, actually in 1990, one of the biggest scientific events in our history so far happened. Scientists from around the world banded together for an unparalleled undertaking to that point, sequencing the entire human genome and setting that out to be a goal. And eventually, thanks to them, we sequenced 3.2 billion base pairs of our genetic code. Truly amazing. I'm talking about the Human Genome Project, which you guys have probably all heard of at Wiles. And thanks to that discovery, we have so many of the advancements we have today. Gene therapies for disease, CRISPR, which we've all heard about, and just understanding key pieces of our evolutionary history that help us understand who we are as human beings. And one of the people who knows the most about that, or knows more about it than almost anybody in the world, sitting right here with us. That's Dr. Eric Lander, the founder of the Broad Institute, one of the principal leaders of the Human Genome Project, former scientific advisor to President Obama. Titles. You're just like, oh, please continue. In a land of big tech and science names here in the greater Boston area, this is one of the biggest. So thank you very much for coming. We're really excited to have you.
It's great to be here.
Absolutely. Thank you.
And I like your home. I haven't been in this space yet.
It's a great space. And, it would be nothing without the lovely, lovely people that inhabit it, of course. But, I really, really enjoy this. And before we get started, just a reminder to all of you guys about the Slido app. Keep the questions coming throughout. I believe the code on the screen was BB610. Yes.
Yes.
And so keep it coming. I'll be able to see on my handy-dandy millennial Samsung Note. Apparently a couple of our hosts had trouble with that, but thankfully I owned one of these, so it won't be a problem. But as we get started, really quickly, I want to know a little bit about you and your background and your roots as a scientist. You were a mathematician by trade, yes?
Well, originally, I'm a kid from Brooklyn, New York.
We're going way back.
Way back. I was a kid from Brooklyn, and one of the amazing things about New York City when I was growing up was specialized science high schools that were open to everybody, public schools. You took an exam, you could go, and I was lucky enough to get to go to one of those, Stuyvesant High School in Manhattan, and I schlepped for an hour on the train to come from the far reaches of Brooklyn to go to Stuyvesant High School, and I got exposed to this whole world of people who did science for a life, and it was really cool. And I think that got me started in many directions, and one of the things I schlepped in for was the math team. Mm-hmm. So I'd show up an hour before school, and we had all these kids who loved math. And I did that every day for 4 years. My last year, I was the captain of the math team, and I loved math. And I went on and went to college. It was Princeton. I was a math major and had a great time. I ended up getting a Rhodes Scholarship, went to Oxford, and did my PhD in math. And it was only then that I realized math was so beautiful, but I didn't actually want to do it as a career.
Yeah.
And so I then cast about to figure out what do I want to do as a career. And, anybody who tells you that their life is some well-planned trajectory where you punch your ticket at different stages is either lying or very young and imagining. But, I didn't know it. And so anyway, the short version of the long story was I somehow talked my way into teaching on the faculty of the Harvard Business School, teaching managerial economics, of which I knew none. But happily, the MBA students knew less. So, and after
as long as they make you look good, right?
It was great. I had a lot of fun. They took teaching really seriously. The business school was very good to me. But after a couple of years of doing it, I also realized that it too wasn't what I wanted to do. Yeah. And I cast about, and through a suggestion of my brother, my younger brother, got interested in biology and began, if you don't know what you're going to do with your life, there is no place in the world better to do it than Boston. Because there are like so many amazing people, and you're going to bump into somebody and something. And I began dropping in on classes here and there, learning about biology, and I got totally captivated. One thing led to another, and at some point, I'll leave out all the details, I bumped into a yeast geneticist at MIT who had some ideas about how you might be able to map the genes for human disease. And I dropped everything else I was doing and began working with him, David Botstein. And a year later, the idea of the Human Genome Project started. And in retrospect,
unbelievably fortuitous.
Totally fortuitous. And of course, the idea of coming with a background in mathematics, some biology, and even having hung out at a business school sounds like just perfect planning to get involved in the Human Genome Project. But it was, of course, utterly random and incredibly lucky. So anyway, that's how I got involved in genetics and the Human Genome Project, was accidentally showing up at the right time in the right place. And the right place was certainly Boston.
You know what's really amazing about that, just don't want to harp on myself too much, right? But it's like, being a biology master's student at the University of Notre Dame, basically deciding at the same, similar way that it wasn't really what I wanted to do. So, I got a master's degree and, worked 3 different jobs, getting into like, sports statistics. Like I really wanted to get into sports statistics and sports journalism or whatever. I went to a conference in New Orleans, met somebody from here at WBUR, and that is the reason I'm talking to you today. It's like the idea of it, everything being completely planned out. You're absolutely right. Like if I had my way, there's like no way I would have originally been here, and yet here I am, and I get to talk to you, which is incredible.
We'll find out, but yeah.
Tell me a little bit about that math background and how it informed what you did and the way of thinking that you went about studying genomics.
Yeah. There's math and there's biology. Math is beautiful and structured, and you lay down axioms and you prove things.
Yeah, I was going to ask you if you're a proof guy.
Well, you can't be in math if you don't prove things, because otherwise, what's the point? It's just opinions. A lot of math, you want to discover patterns and frame what you see going on, but at the end, if you can't prove it, well, how do you know it's right?
Right, and it's like we talk about it, right? The most simple thing in the world is like, that we grow up learning is 2 + 2 = 4. And we all take that for granted, right? That just kind of is what it is. But the idea of somebody had to basically come up with the proof for, yes, because of XYZ and blah, 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 and stringing all of these different, theorems and stuff together, therefore, 2 + 2 = 4. So it's like there's an underlying theory that seems to drive the way that you think about biology and about the kind of your worldview. It seems.
Oh, I mean, look, anybody who's come to appreciate the beauty of mathematics, in a way, wants the world to have a logic to it. Biology has a totally different kind of beauty. It's an inductive beauty. It's the beauty of how you build organisms in strange and unusual ways, and how evolution works. And it's hard to prove anything because there are exceptions to everything. And but what's wonderful is when you can appreciate both totally different kinds of discipline.
Yeah.
The power of thinking like a mathematician, where there's truth and falsity, where there's a perfect logic, where you want completeness, and the incredible beauty of biology, which is constantly unfolding and will unfold, and is, in some sense, a series of accidents. Like a physicist would say, if you heated up the entire universe and cooled it all down, human biology wouldn't turn out the same way. It's a series of frozen accidents. Yes. So you can't say this is the only way life could have happened, or the only, species that could exist. And so there are different kinds of truths about it. And what I feel so lucky at is to speak both languages. And it turns out that those two languages had nothing to say to each other until really the last quarter century. Because, well, I tell this story, David Baltimore.
Oh, please do.
Greatest scientist of his generation, Nobel laureate here in Boston, was the director of the Whitehead Institute, went on to be the president of Caltech. When David built that Whitehead Institute in Kendall Square in 1982, the greatest scientist of his generation made no provision in that building for a computer. There was just like no notion that anything other than your lab notebook, where you would write things in pen so you couldn't erase them, was going to be what biological data was. And at the very last minute, they retrofit the plan to put in a computer room. I think what's happened from then to now is one of the most amazing transformations in biology, because in science, because it's turned out that biology is about data. It's about digital information. Now, you couldn't do anything in biology without vast quantities of data. No student comes in not knowing how to compute. No experiment gets published really without drawing on data that's come from all over the world.
And being able to statistically analyze that data. So you got programs on programs that are meant to be like, look, this is statistically significant, this is not.
Well, you got zillions of databases that you're going to draw on, and you have to analyze, you have to know if it's right. That world is so different, and that transformation, and it's not an accident. It happened because biology itself is about digital information. DNA is just the digital code. It's a 4-letter code, but it's a code of information. That, life wouldn't work if it didn't have its own hard drive where it stored all that information, our chromosomes. And so the union of these two things occurring, say with Human Genome Project and other things around the turn of this century, it's really a seminal thing for the field and pretty exciting.
And how important, we've been touching on it like throughout this kind of entire introduction, how important is it to incorporate that multidisciplinary, collaborative sort of effort? Because we can talk about science sometimes the way that it can be so siloed and so specialized. You get people that are, for example, in the department that I was in, you basically had the ecology people whom the cancer people were like, oh, you're like not real scientists. You don't study rigorous things. And then you would have the ecology people being like, you guys don't even know how to do a t-test. You don't know how to you don't know how to do statistics. What are you doing? And everybody kind of partitions themselves off here. But what you're talking about is taking different languages and getting them to speak to one another for the greater good of science. And it feels so necessary for that. How much of that has shaped your mission?
Oh, tremendously. I mean, the Human Genome Project was seminal as a cultural event in the sociology of science because it was bigger than what any one person could do, what any one lab could do. You couldn't do this unless you brought together people who are biochemists and physicians and mathematicians and engineers and chemists. It was only possible if people broke down the silos. And it worked because we brought together a whole world. There were centers in 6 different countries, 16 different centers, everybody sharing data freely, putting it on the web without any restrictions on it. It brought everybody together because it was necessary to do the job. That's what set this new model. And, it ended up, after the Human Genome Project was done, leading us to create the Broad Institute here. The Broad is this connector. It's an institution itself, but it's the Broad Institute of MIT and Harvard, also called the Broad Institute of Harvard and MIT. And it also involves 5 hospitals here in Boston as well, all working together. And there aren't departments in it. It has all of these computational people and mathematical people, and it's got chemists and engineers and everybody, because it's turned out that the Human Genome Project wasn't an anomaly. It became the rule that to take on really important problems in medicine, you had to drop all this pretense of I'm over here in my silo, you're in you actually needed somebody who knew what a t-test is, whatever a t-test is. Don't worry, you don't need to know. But somebody had to know what a t-test was, and somebody had to know machine learning, and somebody had to know cloning, and somebody had, and they all had to talk to each other. That is the most fun. And the Broad, because it's this connector across the most amazing city in the known universe in biomedicine, is such a cool place to be because everybody is constantly coming and going. The Broad is part of all these institutions, and many of the faculty have full-time labs at these institutions, but they also have a lab at the Broad. And so it's really just this magnet that pulls people together.
And the Broad Institute, by the way, turns 15 years old this year, which is
July 1st.
Hey, there
Come
we go.
to the birthday party.
Yeah, exactly.
Yeah.
Counting down. We got like what, 3.5 weeks? 2.5 weeks?
Yeah, something like that.
Yeah. So I heard you're going to be speaking at that as well. So if you guys are interested in more of this, you guys should totally check that out.
Oh, we're even going to have a whole series of Broad at 15 public lectures in the same spirit of community engagement to talk about what's gone on in the last 15 years and what might go on in the next 15.
That would be excellent. And why has Boston become this hotbed of activity for biomedical enterprise in your mind?
Well, you've got to start with universities. It's got pretty good universities. Mm-hmm. And those universities produce amazing young people. And the secret to all science is young people, because young people aren't.
All my young people here.
Yeah,
it's all about you guys.
No, look, it is because the thing is, young people come along and they're not impressed with what came before. They say, "Oh, I could do that better," or "Why haven't you solved that?" And that's the root of all progress. It's just fantastic to live in a place. I teach students from MIT and Harvard. I have in my lab. And they'll say, it's great you did that, but look, the questions really are the ones ahead. So it keeps it young. It keeps it moving. They're incredibly ambitious and in a very good way. And they want to change the world. They just aren't satisfied with where things are. So that's the root, is an amazing community of incredible young people who just want to keep pushing boundaries. And then Boston has these amazing hospitals. It's got the best hospitals in the world. Mass General Hospital is MGH is said by the people there to be man's greatest hospital. But, there's the Brigham and the Dana-Farber Cancer Institute and whatever. Any one of these plopped down in any other city would be the leading hospital in that city. But we have all of these things here.
Yeah.
So that and the universities led this to be one of the two hubs in the world for the biotech revolution, at starting biotech companies here. And then all of those pieces made it necessary about 15 years ago for every pharmaceutical company to migrate to Boston. It used to be pharmaceutical companies were in New Jersey. That was the head of pharmaceutical companies. And you know why that was? Pharmaceutical companies originally came out of chemical companies. And if you've ever driven on the Jersey Turnpike past Elizabeth, and you see anyway, there's a lot of chemical industry there, and that's why you had a lot of pharmaceutical companies. But they've realized in this century that you got to be connected to biology and to medicine, and so I think every last pharmaceutical company has built a major headquarters here, and then it becomes this amazing ecosystem. And then on top of it, computers.
Yeah.
This region has played a huge role in the birth of computers. And while Silicon Valley has outstripped the Boston area, it's still one of the best places in the world. So all of those pieces being together in 15 minutes to get from one place to another place across town, if there's not too much traffic.
Which there always is.
You can bike. If you bike, it's both green and faster. All of that, there's no place else in the world that has all those things. And that's why this has become the hotbed for all of that.
That's pretty incredible to hear it kind of put in those terms. I want to touch on something that you mentioned regarding young people and the idea of it all starts with basically a question. Why haven't you looked at that? Or just, well, I think this is interesting. Let me pursue this. Has anybody done this? No, I'm going to do it. And that really is such an interesting and really essential part of discovery, as you mentioned. But it also isn't limited to young people. So I'm interested to know about you. In your mind, what questions are you thinking about that you want to see answered? What's driving you? What are the possibilities that you are exploring?
Well, I think deep down in my mathematical roots, what I loved about the Human Genome Project was the idea that we could get the comprehensive picture of all the genetic information. Now, why do I care about that? I care about that because you can be systematic. Before the Human Genome Project, you want to find the gene for cystic fibrosis, the gene for muscular dystrophy, the gene for some other rare genetic disease. People would sit around and think up a hypothesis. Oh, I bet muscular dystrophy must be caused by this protein or in that cell or this or that. It turns out we're terrible guessers. So, people, they would sound very sophisticated. I have a hypothesis that the disease is caused by X. But the truth is you're just guessing. And usually you don't have a clue what it's really about. What the Human Genome Project did was it let you be systematic. It said, look, there are only 20,000 genes in the genome. We can trace the inheritance of every one of them in a family, see which genes track along with the inheritance of the disease, look at those, sequence systematically, and figure out which ones have a mutation in patients. No guesswork. Guaranteed to get you to an answer. I kind of like that it's sort of, the periodic table of the elements. You all know the periodic table of the elements. There's only 100 and some odd elements. There's no more. You want to make a molecule? That's what you got. You're going to explain it in terms of those. You want to make a cell? You got yourself 21,400 genes or thereabouts. Those are the elements in the periodic table of the genome. And that's what you got to work with. So I love that. I love thinking that we could proceed systematically. Because of that, I like thinking about what's the next question. So when the Human Genome Project was done, we started asking, how much genetic variation is there in the human population? If I pick two random people in the audience, how much does your human DNA differ from each other? And it turns out you're 99.9% identical. But that's still one letter difference every 1,000. So that means that between any two people, there are 3 million differences. Now, what if I take the next person and the next person? We start adding it up. Could we build a collection of all the, say, common genetic variation in this room or in this city or in this world? The answer is you can. And so we began doing that. And it turns out there's only tens of millions of common genetic variants. And back in the late 1990s, that seemed like an infinitely hard project.
And it sounds like when you say it, like, no, there's just like tens of millions of like variations. That's not that big a deal. It sounds like a lot.
It was a lot.
You're hearing millions and you're like, oh my God.
But in the late 1990s, it was absurdly large.
Yeah.
And today, you just open your iPhone, not right now, please, but open and you can access all those. So human genome sequence, check. All common genetic variation in the population, check. Now, what about, here's an exciting thing that's going on today that excites me a lot, so I'm building up to it, is same thing with regard to cells. What are all the cells in your body? Now, you would have thought that we know the answer to that question. Everybody thinks in the textbook, it tells us how many cell types there are. Some textbooks actually say there are 200 cell types. They made that up. Nobody has a clue. Now, folks have been staring down the barrel of a microscope for a very long time, and they describe cell types by their shapes and maybe other properties. And yet, how do we know that there aren't other cell types or things that look the same aren't actually fundamentally different? Actually, another famous person in the city, Sidney Farber, after whom the Dana-Farber is named, very famously found that childhood leukemia was actually two totally different diseases that had been lumped together. One called AML, one called ALL, and those cell types were totally different, but nobody had seen it till Sidney was so inspired that he was able to find those differences between those cell types. Well, I hate that, because that took him 40 years to establish those differences reliably, and it involved guesswork. Could we just do that systematically? Just find all the cell types in the human body. Well, it turns out you can. A colleague of mine at the Broad, a woman named Aviv Regev, and her colleagues worked out a way to take individual cells and read out the genes that are turned on or turned off in that cell.
Okay.
So imagine one cell. Got 20,000 genes. These ones are on, these ones are off. Next cell. These ones are on and those ones are off. Next cell, next cell, next cell. This may seem a little crazy, but bear with me. Every cell has a list, 20,000 long, of which genes are on and off and by how much. For the mathematicians in the audience, it's a vector in 20,000 dimensional space. That's a point in 20,000 dimensional space. If you don't do 20,000 dimensional space, think 3-dimensional space. It's a point somewhere.
So basically, if I might, so it's essentially check which ones are, go down your list, which ones are on, which ones are off. And then if, you have a couple that are identical, perhaps, like these two cells have the exact
same pattern. And these guys have the same pattern.
Yeah, and it's like they occupy like the same point.
In space, there are 2 points right near each other. So your whole body, all those cells are points in this space of gene expression. And what does it mean to be a certain type of liver cell, a Kupfer cell? It means they're points near each other, similar patterns of gene expression. The eye. People spend 25 years studying the back of your eye, the retina, to find cell types. Well, when they began looking at this gene expression stuff, they found out there are twice as many cell types as anybody had ever guessed. Well, this grew from an idea here in Boston 5, 6, 7 years ago to now an international project that involves more than 55 countries, 4,000 labs, that is going to build over the next 5 years a complete atlas of all human cells called, fittingly, the Human Cell Atlas. I like that because
common sense.
It's a good name. You remembers it, right? So it means that when we want to describe a disease now, some disease liver or some disease on the skin, we can now sequence those cells' gene expression and see how it differs from a reference. So it's kind of the Human Genome Project for this decade. And there's a whole bunch of young people who have come together for that Human Genome Project, that periodic table of the cells. And there's even folks hanging around Boston now that are beginning to talk about the periodic table of all the computer programs that cells know how to run. What is that? I mean, DNA runs programs. Different programs to cause a cell to divide, to make a cell into a certain kind of eye cell. There's only a finite number of programs in the programming code book there. There are young people running around now saying, well, we're going to find them all, and we're going to recognize disease in terms of those. So the transformation goes from when nobody thought there was data, meaningful computation, information in biology, to a world, I don't know, 5 years, 10 years, 15 years from now, but not so far from now, where we know all the human genome, we know all the variation in the population, we know all the cells and know how to read them out by their gene expression patterns. We even know the programs and how they run, so we can think about treating disease by tweaking those programs. And none of this is easy, and I'm not Pollyanna that this magically cures all disease, but what I will say is from the year 2050, people looking back will say, how in the world did we imagine we were going to take on disease without knowing that? That is what excites me about this fusion of data science and life science coming together, is it gives us now the tools for a next generation to approach things systematically and rationally. And that doesn't mean you cure everything. I keep saying that.
We're going to get to that.
But it does mean that you have a rational chance to go at it.
Yeah, and
Anyway, sorry for the long answer, but
well,
this is sort of roughly my life, so I got to give it like 5 minutes.
Say, we wanted to know what's on your mind. There you go.
That's the problem. You ask, you get it. Yeah.
Yeah. Now, while we're on that, right? We talked about this on the phone. The idea that somehow somebody got the idea that the Human Genome Project was going to be a magic bullet that meant we were going to cure all disease. And we were on the phone, and he just kind of almost jumped through the phone at me. He was just like, we did not say that. He's just looking around like, that was not me.
That's not me.
So it seems like... Was it a breakdown in communication from a scientist to somebody about this? Did somebody jump the gun? Or was this something that people just made a leap? Like, oh, we're going to find out what our genetic code looks like. Is that going to solve everything? And then people ran with it. Where was the breakdown there?
Well, there's enough blame to go around, I think. We can start with all the journalistic coverage around the time of the Human Genome Project was, to get attention for your story, you had to say, what would this mean for people? And so it's very natural to say, this has the potential to lead to cures for everything. And it does have the potential to lead for cures for everything, but like a ways out. And so then people, but of course, nobody wants to run a lead on the story that says, eventually, someday might lead to cures for everything. And so it starts getting telescoped into, in the next decade, we're going to see. And scientists get blamed for that too, because I think scientists are enthusiastic about what they do and sometimes don't have a long enough historical perspective about how science is transformative in the long term, but it doesn't just happen like that. The Human Genome Project meant we had read out 3 billion letters of our genetic code. We didn't understand it. It was if you had received the Encyclopedia Britannica in Uzbek. And you say, I have all this knowledge about the world, but I don't speak Uzbek. And now I'm going to become wise. No, we recognize that having all the sequence of the human genome didn't mean that you knew the cause of any particular disease, like which gene might be responsible or which 100 genes might contribute. And then it certainly didn't mean, even if you knew those, that you understood how it affected the cells to give rise to that disease. Why did the muscular dystrophy gene give rise to muscular dystrophy? Or what about the genes that affect Alzheimer's? And then, how were you going to cure it?
Yeah.
And then, even if you knew how you thought you were going to cure it, it's another 10 years to take a treatment into the development of molecules, into clinical trials, into an approval at the FDA. So anybody who was imagining that going from the reading of the human genome to cures for everything in, say, 20 years was smoking something, because there's no way you could possibly do that. Now, I am an optimist. I believe that this is the inexorable path, but I'm also a realistic optimist. I look at the incredible power from when scientists came up with the germ theory of infectious disease, the idea that infectious diseases were caused by bacteria, which was big news at some point. It took about 65 years to get from there to penicillin. 65 years. But when we got penicillin, within a decade, penicillin was cheap, and people were living who would have died, and it's made a huge transformation. We could get into antibiotic resistance and the rise of all that separately, but what an amazing transformation. You can get into cancer. The deep understanding that there were genes that drove cancer was 1980, these discoveries. Well, it's been about 40 years. We're beginning to see really powerful treatments come along, and we're still nowhere like at the point where we can say we've cured cancer.
Right, and I remember seeing, you spoke about this recently, which is that we can't even begin talking about cures for cancer for at least another decade, and I think you said in this article it was probably closer to 40 years or something like that.
Well, what I said, this was an article I wrote, it was an op-ed in the Boston Globe called, Hype versus Hope. It is the case that we're seeing cures come along. Sidney Farber, childhood cancers, leukemias, amazing. We can actually take childhood leukemias, blood cancers, that were 90% lethal. Now they're less than 10% lethal because we can cure them in the vast majority of those cases. That's incredible. But it's piece by piece, steady progress to move forward. We are seeing amazing things with drugs like Gleevec that I knew somebody during the later stages of the Human Genome Project who'd been diagnosed with a particular completely fatal tumor. He's still alive because Gleevec came along at just the right time, and it treated that particular genetic cause. Now we're seeing immunotherapies. So I don't mean to say there's not going to be progress along the way. I mean that that sweeping statements of we're going to cure cancer is not what it's going to look like.
Yeah.
It's going to be steady progress. If we get to mid-century and half of cancers that would have been fatal are now treatable disease, manageable disease, and then it goes from there to the next and there to the next, that's amazing because every bit of medical progress like this is permanent progress. It is the work of this generation and the next generation to move that forward. And so I find that incredibly hopeful, incredibly optimistic. We will see progress. And I really strongly oppose the idea of making false promises about how fast that will come, because I think it's mind-blowing enough that it's coming at a steady pace. And I think if you make false promises, you lose people's trust. I don't think there's anything we have to apologize for if by mid-century we can get half of cancers that would have been fatal to now be perfectly treatable diseases. That would be amazing.
Yeah, absolutely. And really quickly, just to remind everybody to jump on Slido, include your questions. I've seen
What's
a couple
the
of them
password?
already.
Shit.
Yeah, there you go.
Sorry. That was an easy question. I'll ask harder questions later.
Exactly. So you mentioned in there a couple of interesting points, right? And so as I think about it, how do we communicate to people as scientists, me as a former scientist, you as a current one, what that process looks like? Because I think that everybody here has just, heard this and probably knows it, right? Scientific discoveries take a long time, but for people who aren't up on the science, for just like your average Joe who just opens up the paper one day and sees some story about cancer. I mean, as a journalist now, I have read scientific articles for many years, and now I'm thinking of it in terms of like an editor or producer, and I'll be like, oh wow, that article explained that really well. And I'll read some headlines like, oh God, like they're doing the false promise thing. How do we as scientists help ensure that doesn't happen as much as it's possible? How can we be better about that?
Start by being honest about everything. I mean, I think the true story is inspiring. It's just extraordinary. Look at anything that works today in medicine and look backward at the true story that gave rise to it. Take HIV. When HIV was a death sentence, and then we developed anti-HIV drugs. And that was a collaboration of scientists and HIV activists and many others. And it was an amazing transformation. We still don't have an HIV vaccine, but there are people working on it, and they have ideas for it. And because we saw the progress with the HIV drugs, we're willing to credit that people might be able to come through an HIV vaccine. We've got a lot of folks here in Boston who work on that. There's a whole institute devoted to that. I think it's got to start by people understanding what this journey is, that there are a lot of people dedicated. Basically, it's the power of understanding. Understanding the basis of disease, whether it's understanding HIV for AIDS or understanding genetic bases that contribute to schizophrenia or understanding what actually causes Alzheimer's, unlocks possibilities. The alternative is ignorance. Try ignorance. It doesn't work. There have been a handful of times people have cured diseases by dumb luck. But luck is not a plan. It is the case that understanding has consistently made disease yield over time. I think if we can communicate that story, that we've now cracked open the first genetic pathway, developmental pathway that gives rise to schizophrenia, which actually happened here in Boston about 4 or 5 years ago. We have a center at the Broad called the Stanley Center for Psychiatric Disease, where 7, 8 years ago, the number of genes we knew that contribute to schizophrenia was 0. And today it's 260. And they're beginning to fall into pathways, and we're beginning to get these pieces. And I can't promise you when that's going to lead to a cure for schizophrenia, but I know that without that kind of information, we're never going to get
possible,
there.
Yeah.
So to me, this is the story we have to be able to tell as scientists again and again, that that real hope comes from real understanding, building block on top of block. And I know, because I have had friends who have died of cancer, that it's going to come too late for some people. And it may come for our children. And if we deliver this for our children and our children's children, again, there's no apology for that. We just have to get up and work as hard as we can so it gets here as soon as possible. I think it's a fabulous story, and I think people understand it when you tell it honestly.
I think that your discussion about real understanding, but also the flip side of it being ignorance, that is, to me anyway, one of the fundamental dangers that faces, one of the fundamental challenges that faces the scientific community in our quest to educate people and promote understanding. So we talked about this a little bit, that you were an advisor to President Obama. He had a president's scientific, he had scientific council.
President's Council of Science, President's Council of Advisors on Science and Technology, PCAST. So then you can just say PCAST.
There we go. So he had PCAST.
He had PCAST, yeah.
Our current administration, and I mean, you can talk about perhaps as much as you're able, what advice there is going on there, but we've seen examples of climate science, being denied. We've seen controversial things that seem to go a little bit towards perhaps religious understandings, like fetal tissue bans and things like that. What do you think is going on a grand level right now with science in this country? Do you think that there is a problem of understanding that is not being addressed, and perhaps people don't want to address it? I mean, what do you think's happening here?
Oh, that's a small question. Yeah.
Sorry. Yeah, definitely. Took a while to unwind that one.
No. It's I didn't mind the length of the question. It's a question of how to answer it, because so many things are packed in that. Let me start with one. Ignorance is one thing. Willful ignorance is another thing. One aspect of what goes on in the world is a desire not to confront the truth. I think if you're willing to confront the truth, you'll change your opinion in the face of evidence. You're a scientist. That's all it really takes to be a scientist, is to say, I might be wrong. And show me. Now, I might be hard to convince. I might need more evidence. But if you're not willing to be convinced by evidence, you're an anti-scientist. It's the opposite, because when someone, let's just take climate change, there is no question that we are observing climate change. It's not tough. You put up enough carbon dioxide lets light through, which when it turns into heat doesn't go through. Anybody who owns a greenhouse understands why it's warm and why you can grow tomatoes in a greenhouse. And carbon dioxide is a greenhouse gas because it does the same thing as the glass on your greenhouse. We can measure the increased temperatures. We can measure, glacial retreats. We can measure 1,000 things. When I go in the summer to Lake Winnipesaukee, to the ice cream store on Lake Winnipesaukee, and they have right up on the counter where I buy my ice cream, it has the date of the thaw of Alton Bay in New Hampshire for the last 130 years. I just ran my finger down and said, from that alone, you can see that this part of New Hampshire has been warming because the thaw is becoming earlier and earlier at Lake Winnipesaukee. You could give 1,000 such reasons, and yet you have people say, oh, well, we don't really know, or it's just natural, or whatever, or, well, scientists, they're an interest group. It's very frustrating because this isn't being said because anybody's truly in doubt. It's being said because the conclusion is very inconvenient. And I think this is a problem. You can't practice science and you can't get the benefits of science for yourself, your children, your society, unless you're willing to confront things and say, I might be wrong. And if you're coming in with some prior point of view that you are unwilling to change because it might affect your company in some way, you're not practicing science. And science has turned out to be the most transformative force for good, because understanding is the foundation of a lot of good. There are a lot of other things that are important, but if you don't understand how the world is working, you can't build on that. You can't improve the world. So it's not that complicated. Usually there is some self-interest that prevents people from truly wanting to confront this. You know, I feel differently about, some of these issues on stem cell research. I think the idea of banning stem cell research, as just happened with the federal government, is a very bad idea medically, because it's going to cut us off from doing a lot of things that can't be done any other way. But I will admit, there's at least a set of people who are doing that out of deeply held ethical beliefs. I don't agree with those beliefs. I think as an ethical balance, the fact that there are tens of thousands of embryonic tissues in freezers today means that it's unethical not to use them when they can help. I think, to me, it's not a question of even a close ethical balance, because they exist. And to tell the NIH cells that you're using today to try to work on diseases, you must stop using them because I'm unhappy about some aspect of their origin, I don't get the ethical idea there. There are valid discussions in this country and less valid discussions, but there I view this as a utilitarian balance of, I can't see why we wouldn't do this when it's actually helping to save lives and make new treatments, and it isn't replaceable by other things.
Right.
So I think, you've given a whole lot of different questions in there. Why do people deny certain things? It's inconvenient. Some of these other things flow out of certain ethical beliefs, and we ought to sit down and have those conversations as which is more unethical. But it's complicated. We have an incredible amount of work to do to bring people along to understand that this culture of thinking scientifically is the best hope for our children, that this produces the power to change the world in ways that are good. But it's not natural. Many people aren't brought up to think this way. So I understand that we do a pretty crummy job often of teaching this. So I don't have any magic answers on how it's going to happen.
Yeah.
We're going to have to keep repeating it and repeating it and repeating it and saying, I want to do this because I want my kids to have a better world. Denying something, it's not going to produce a better world.
Yeah. And by the way, great job untangling that beast of 5 different questions that I had in there. Well done. You mentioned science as a force of good, and we've talked about all the great things that it can do, but some of the discussion is also marred by some of these ethical questions where people perhaps are crossing a line. And the one that everybody knows about and has thought about is the CRISPR babies experiment in China, where genetically editing 2 twin girls with the idea of helping confer immunity to HIV, but the consequences of that, the potential consequences, which we might not even know everything about, is what made the scientific community just jump out in backlash. What was your thought when you heard about what had happened?
Oh, so many thoughts. Let's try to unpack it a little bit for everybody. So I assume everybody who walks on a random street in Boston fully understands CRISPR, right? Because it's one of those. So this idea of editing the genome in cells is a very powerful technology. It was discovered by scientists over the course of 20 years that bacteria had invented this way to edit genes more than 1 billion years ago. And by sequencing bacteria, scientists found it and then figured out how it worked, understanding, and then were able to put it to use and be able to edit genes and cells. And that's getting used for a lot of pretty amazing ideas. Cure a gene for blindness in the eye, for retinitis pigmentosum, or fix a gene for muscular dystrophy, or fix a gene for familial hypercholesterolemia, what's called somatic gene therapy, changing the genes in a particular organ in your body. But it also raises the possibility of editing babies, producing babies that have new genetic sequences inserted in them. And so every powerful new technology also raises important ethical issues, and they're part and parcel of them. There are these amazing technologies that might treat all sorts of diseases, and then it gets into the question of, do we want to have genetically modified babies? Maybe for some purposes, maybe there are some cases where you might change a gene that will prevent a kid from having a really severe genetic disease. Of course, there might be alternative ways to do that. But then you could go even further. Maybe people will say, oh, I'm going to improve the human race. I'm going to make improve, that was air quotes there, the human race, because I'm going to confer properties like immunity to HIV by knocking out a particular gene that the virus needs to get into cells. That was the idea of this guy in Hong Kong. Or, I don't know, I might have an idea for making everybody more intelligent because I think that if I change these genes, everybody will be more intelligent. Or I might not really know, but I might have a really good advertising firm that'll make it seem like that. Because, IVF clinics aren't really that all well regulated in this country. Or actually, there's a good gene, the erythropoietin receptor, where there was a Finnish guy who had a mutation that made it active all the time. And he won 7 gold medals in the Olympics in endurance sports because he naturally had high levels of red blood cells there. So if you're sports-minded, maybe, that's something to consider. The point is it ranges all the way over there. As the stewards of the human race, where do we want to draw these lines?
Yeah.
Do we want to start at all? Do we want to go a little bit and draw the line there? So the guy in Hong Kong, to come back to Dr. He Jiankui, gave us the easiest case in the world. He conducted a secret experiment without proper institutional review. He edited embryos, produced mutations that were not the intended mutation. Deciding whether to put them back in, he decided to ask the parents who knew nothing about molecular biology what they thought and decided to put it back in because of that. And he did this for this HIV protection because the father had HIV. But the father was never going to pass HIV to the kids. So
they were not really in any increased danger.
No, there were no risk at all of getting HIV from the father. And later in life, well, oh my God, who knows where we'll be there. But also it turns out that making genetic changes in the human genome is not a free lunch. You knock out that gene, goes by the name CCR5, you do actually reduce the risk of contracting HIV. You also increase the risk of dying of encephalopathy if you get West Nile virus.
And so
and then a week ago was published the paper that reports,
I saw this.
Oh yeah, individuals who have both copies of that gene knocked out have a shorter lifespan. Now you could say, well, I didn't know. I think that's the point, is
you didn't know.
You didn't know. What in the world were you thinking, making permanent changes to a baby that would be passed on to future generations? Are we ready to start modifying the human genome? I don't know, but I think we have to approach it with a great deal of humility. And if there are cases to be considered, they're going to be very limited cases. And I should say, the National Academy of Sciences in the U.S. and the National Academy of Medicine and the Royal Society and a bunch of other international societies have organized a commission to look at some of these questions. And I am a member of this commission. It hasn't started meeting yet. And I have a very open mind to what the answers might be, but I have a very strong opinion that we better be mighty careful about how we do it. And we'll have lots of discussions about it. And, I've thought hard about it. I've written about the topic. These are choices we collectively have to make as societies. Almost every one of these cool new technologies today, whether it's CRISPR CRISPR gene editing or AI and various aspects of AI, they offer amazing potential upsides, but they offer potentially dystopian downsides. And whether we like it or not, we are all stewards of this brave new planet that we've got. And we got to go make choices about how we want to govern these things.
Absolutely. And I think, kind of that responsibility, I think you've called for a moratorium on CRISPR editing, in live subjects for, I believe, the next 5 years. I've seen a couple of people who were like, well, we already had a moratorium. We should just have strict regulation. Is that because essentially the thought was, well, people know we shouldn't be doing this. But if they knew they shouldn't be doing this, then why did it happen?
Well, look, I mean, it's always what was done in Hong Kong was unethical, outrageous, inappropriate. But it's also true that one rogue scientist doing something wrong isn't what changes the world. It's very bad for those particular girls to whom it was done. But what worries me much more is what are the policies we're going to choose to adopt as societies. I don't know whether any moratorium, I doubt a moratorium would prevent one rogue actor from doing this who wanted to get famous about this or who thought it was a good thing. I think the real thing we have to focus on is not how do we prevent one rogue actor. That's what laws are for. If he should have, I believe, violated Chinese laws and should be punished for that. What we really have to do is say, what are our policies going forward? Are we going to say this can be done for anything, for a limited circumstance? So actually my interest in some time to think about that question is much more for society to decide what consensus it has about how to go forward. People who do these experiments like the guy did in China, in the United States, that would have been illegal. Nobody's quite sure in this case with Chinese law. They will kind of figure it out. They should be illegal. It's the social choices that we make that matter, and we got to give a little bit of time. Think to things like Facebook. I think Mark Zuckerberg, with good intention, said, "Bring the world together." What could possibly go wrong? And it turned out things could possibly go wrong, and it's worth spending time when you think about science and as a scientist to think what could possibly go right and what could possibly go wrong. And it's not anti-science to ask the question, what could possibly go wrong? It's actually part of the scientist's obligation and part of your obligation as a society. We got to have enough of a conversation about it so we kind of steer ourselves so we get most of the benefits and not too much of the downside.
Absolutely. All right. I'm going to jump into some questions now. We're going to hop over to the Slido app. I believe they're supposed to appear on the screen.
What happens here? Wow.
All right. Yeah, I know. I'm going to be reading them off of this so that I'm not staring upward at the ceiling like that. It's a little crazy. So I'm down here at the bottom, actually. Let me hop up to the top. So I like this question. Now that comprehensive gene therapy is in the works, what are your thoughts on potentially creating health inequities between insured and uninsured people? So are some people going to be left behind as we transition to this idea of gene therapy? Some people can afford it, some people can't. And how do we bridge that? That was my addition at the end.
Oh, good, because the answer to the first question is yes. With every new medical technology, because of the way our healthcare system is configured, some people are left behind. And that is a real problem. And it's a choice we make about how we choose to fund healthcare. It's not unique to gene therapy, and it doesn't make it any better or worse for gene therapy that that's going to be the case. What do we do about it? You're asking a fundamental question about how we choose to organize our healthcare system and give access and equity to all of healthcare. There are so many things that need to be fixed, and we won't have enough time to do all of them.
Yeah.
But let me start with the tension between, and I'm going to try to be very understanding of all the parts of the ecosystem. Innovation is expensive. You want to develop a new drug, you want to develop a new therapy, it actually really truly does cost a lot of money. I think we can find ways to make it cost less, and we really have to do that, but it's not cheap. So that means innovations somehow have to recover their costs.
Yeah.
All right. So we've chosen here to have high drug prices for a while during a patent period to help recover costs, to create the private incentives for people to make new therapies. I might be okay with that if the costs then plummeted after that patent period. Yet they don't seem to plummet. Or
because people have, been like, hey, high drug prices makes us a lot of money. Why would we drop them?
Well, no. But I mean, in theory, Economics 101, the textbook says that when it's off patent, generic drug manufacturers should come in and instead of producing it at the cost of at pricing at value, they'll price at cost.
Right.
Because
so
once you have two or three of them, they drive it down. Adam Smith, Invisible Hand,
right,
all that.
Exactly.
But it doesn't happen.
That's the theory. Yeah.
That's the theory.
In practice,
we don't see it happening. So there are a lot of things that are broken. There have been examples of companies discouraging generic drug companies from coming into the market, paying them off to do that. The U.S. government doesn't allow the U.S. government to negotiate drug prices. I don't see the logic of that one exactly, but all right. You just got to ask, why isn't it functioning like a typical market? So if you told me that there was unequal access for the limited period of patent coverage to pay that back the innovation. Now, this was not the case with penicillin. Penicillin cost a lot of money for the first couple of years. Those were very expensive, and then it plummeted down to pennies. I would at least like to see the laws of economics apply to this stuff. And it's complicated. Even when you have generic drugs, and we saw the example of a couple drug manufacturers with EpiPens and others jack up the prices really high because they were the monopoly supplier of something that in principle was generic, but to compete with them would take 3 or 4 years to get a competitor on the market. We have a lot of fixing to do throughout the healthcare system. I'm not opposed to the idea of powerful new innovations, even expensive new innovations, and I'm realistic enough to know they may not get equitably distributed at the beginning because of many aspects of our system, but I can't justify why they don't, over time, become equitably distributed across the board. And I think that's the deeper crime of our healthcare system.
I can see the logician in you.
Right.
It's that you want it to follow that system because that is the way it should be, and the fact that in practice it doesn't work that way is just like it kind of grates you. I can see.
Well, I mean, look, it grates me in terms of logic, but we're talking about life and death.
Yes,
it grates me much more in terms of life and death. That these rules of logic that are used to justify the system there aren't delivering the result. And it's not about, clicks on a website or this or that. It's about who actually gets proper treatment. So we all ought to be outraged about that and demand that we have a system that still incents innovation and yet one that ends up distributing care over time equitably.
Absolutely. Next question. How do we find a balance between big data and deep data and ensure that we're leveraging the best of both? So if you could actually...
So what's deep data?
Yeah. So that's actually something I would like to know.
But don't ask me. I didn't ask the question.
Yeah, this is true. This one is an anonymous question.
It's an anonymous question.
Yeah. Mystery person.
Deep data. Oh, great. Okay. So you're willing to de-anonymize yourself.
Yeah, if you don't mind.
Can everybody hear Jolynn? Here, I'm coming down to Jolynn for a moment.
Oh, I can do it. See, we're getting a true city space experience tonight.
So deep data.
Put that up close to your mouth.
Deep data is when you take a very narrow focus and hone in on a very particular system and understand all of the minute complexities that are associated with that.
Got it.
Yeah.
Oh. Thank you. I like that definition.
Yeah.
Thank you very much.
That's very cool.
What do you do?
I'm a first-year chemical biology graduate student at MIT.
Oh.
All right.
A ringer. Well done. Excellent. And what do you want to work on? Like, what interests you?
I'm interested in immunotherapy development.
All right. Well, I'm glad I asked. That was very good. All right. So
showing off his skills as an interviewer tonight.
That wasn't that hard, actually. It's it's a really interesting thing of where one goes deep, because there's some things that you can't learn if you don't go deep. We're in an age of these big data where you collect lots of noisy, messy data across huge numbers of things, and you can pick out patterns you couldn't see any other way. And it gets a lot of attention because scraping data off the internet or off, devices, Fitbits, other things produces a tremendous amount of noisy data. And there are a lot of machine learning techniques that let you learn from that. But I love the idea of deep data because science makes a lot of progress by having a limited number of models that we deeply understand. When nobody understood how any gene was regulated at all in the early 1960s, people worked out one gene in E. coli. It goes by the name the lac operon. And that one thing worked out deeply, provided a model that applied to 1,000 things. And then a few more things were worked out. So I love the idea that the kind of data collection projects we have to do are ones that go horizontally and then drill down deep to study like one cell type in gory detail. We were sitting around my lab today. I got about 12 people from different groups, and we were talking about the future of human genetics and what kind of data we needed. And there's exactly this tension between let's get certain things across every cell type in the whole human body, and then shouldn't we take just like blood cells where we have easy access to them and they can be our model system and go really deep? I think there's an art in doing that balance, and maybe not enough attention to this deep data, and I've never heard anybody use that name for it, so I like it a lot.
Yeah, thank you very much.
Great question.
And thank you for identifying yourself, Jolynn. That was great. And this the magical city space moment that I have yet to encounter. I'm really glad that happened. So yeah, on to the next question. Man, this is going great. Given the importance of, why is Slido, oh man, did I just do a thing that I said I was never going to do? Anyway, I started refreshing my browser. But in any case, given the importance of early education in your career, how would you characterize the state of science education at the high school level? So in particular, right, we're talking about the pipeline now. How are we going to get younger students at a level where they can think deeply and come up with some of these innovations and stuff on their own? Are we doing a good job of that?
We have two fundamental problems. One is equity. When we think about going into science, for example, if you don't know algebra, you're kind of boxed out. If you don't know some just simple, basic mathematical things. And yet, when we look at education in mathematics across the country, it is so uneven across different groups, different parts of the country, across different ethnic and racial groups, across people living in certain inner city schools. And when you realize that that cuts off all of these STEM careers, if you didn't get that, it's hard to go back and fix that. You can do it, but it's really hard. That's the first thing, is we have an issue of participation. If half this country can't participate because they don't even get the fundamental education, and we are tying one of our hands behind our backs as a nation when we are going to have to be competing in the 21st century with lots of other nations. And so I think it's a matter of national security that we think about, and economic security, that we think about equity with regard to these foundational things that let you get in. That's one. The other problem is in high schools, we often, very frequently, teach science as if it's about the answers in the back of the book.
Yes, yeah, that is one thing that drives me insane. I was so my wife and I have done STEM outreach before, and we actually did some stuff when we were at Notre Dame together, and really tried to center it around hands-on activities and build something, and then teach us about what you built. Teach us about the concept, because in the end, if it's all about just getting the answer and you're literally flipping, and you got like little science, questions in your book and you're flipping to the back of the book for the answer, and that's how you learn. It literally just, there's nothing that's being conceptualized. There's no incentive to think more deeply about the problems. There's no reason to ask the questions, right? Because you're just looking for the 1 or 2 word answer to it.
Well, I mean, even when I was in college and took a physics lab, we were supposed to measure the speed of light. And we knew what the answer was. And if we didn't get it, the task was to figure out how to fudge the experiment so you could get closer to the speed of light.
I did that experiment too. I know exactly what
I think it teaches the wrong things. Seriously, discovery of anything is a powerful addictive drug. Anyone who's discovered something and realizes, oh my God, I discovered something, wants to do it again. I built something. I discovered something. That's why people go into science. I would be happy if they learned a quarter as many facts, but they learned how to discover something. And that's how we have to arrange science, because if you get addicted to learning and understanding and discovering, oh my God. So I used to teach National Science Foundation's summer math program. This was many years ago, so when I was in college. And we tried to get the kids to discover mathematical things, and they did. And it's pretty cool that they wanted to know, oh, but how does that generalize? And what's the next thing? And I think anybody who's gone into science has at some point gotten hooked by the power of realizing you have the power to learn something that somebody didn't know before, or at least all your friends didn't know before, and you brought that piece of knowledge into the world. So I think these are the two problems right now, is we do far too little of exposing people to what science is really about. It's not about memorizing anything, and it's never about the back of the book. And we don't have equitable access to the foundational tools. That said, the United States still produces the most creative young scientists in the world. It's an amazing system. It's an unequally distributed system, where at the tail of the distribution, we turn out amazing science students here. Why we can't be turning out tons more of them is really the problem.
Yeah, absolutely. This question's been sitting in the queue for a little bit. Do you think that we were naive to assume that junk DNA existed in the human genome? So first, for people who don't know or haven't necessarily familiarized themselves with what junk DNA is, could you explain that?
So,
somewhat succinctly, as we're running out of time.
Sure. Junk DNA is DNA for which you don't know its function. So it's a, someone once described the difference was junk DNA versus garbage DNA. Garbage you throw out. Junk you keep in the attic. And so, but of course, even the junk in the attic, if you have a big pile of junk and there's something sitting on top of it, if suddenly the junk disappeared, that thing would crash to the ground. So that junk has a function. It's holding up that thing right now. And it would be bad if it suddenly disappeared. So it's hard to attach function. The real reason junk got I say this only half facetiously. The junk simply means we don't know what it does.
Yeah.
But the real reason, this should freak you out, half of your DNA or more is an infection of transposable elements that hop around your DNA. I'll just say that again.
Please do.
Your genome got infected more than 1 billion years ago and has continued to be infected by selfish pieces of DNA that copy it themselves to other parts of your genome. You have this little 300-letter thing called SINE, sign, and you got 1 million copies of it in your genome. And to a first-order approximation, you ask, what does it do for me? The answer is nothing. It does for it. It replicates itself. And that's all it takes for things to survive is they replicate themselves.
It's basically like a DNA parasite?
Yeah. Well, but now it turns out
okay,
that occasionally they get co-opted to do good things for you.
Okay.
So sometimes new regulatory elements get built or evolve out of those pieces. And so it turns out, we learned in our own lab some years ago, that some of these things have moved around innovations. When some new regulatory element evolved on one of these things, it copied itself around and it spread this new innovation. One might say that genetic innovation went viral because it actually did go viral. That was, and so maybe it's not a parasite but a symbiont.
Yeah.
Who's to say which ones? The reason this name junk DNA got attached was because the vast majority of these transposable elements that hop around our genome were viewed to be selfish parasites. But of course, even if they're just spacers, like the thing in your attic that's holding up something, the spacing may matter because you may come to depend on it, even if you hadn't intended to. So it turns out function is a hard thing to say that something doesn't have. The only way a biologist feels comfortable that this is functionalist is to take it out and then look at how the organism survives under a large number of circumstances. And after enough testing, which might be millions of years, we feel comfortable saying that's functionalist. So we only joke around about junk DNA. But on the other hand, you gotta, for headlines, it's only 4 letters. It fits really well, so it got a lot of attention.
Hey, 4 letters, 4 base pairs, it's like it all matches. It's perfect. So here's a question that gets at a little of what we've talked about in terms of communication. What is the Broad Institute doing to educate the population in parts of the U.S. where there's less trust and less belief in science in general?
So, people from the Broad Institute, come on these kind of programs, and you will broadcast them to God knows where. That's good.
It will be on YouTube and hopefully viewed many, many, many times.
Well, there you go.
Share this when it comes out, by the way, shameless plug.
Shameless plug. No, I think we try to make sure that many people at the Broad, myself included, but lots of scientists and leaders at the Broad, feel a responsibility to talk about their science, share their science, and listen. It isn't just about educating others, it's about listening as well. So I think it's very easy to say scientists should educate other people. Scientists need to be educated as well. So we give talks, we try to put things out. I write op-eds, I give public talks. All those things are part of what it means to be a responsible scientist. Now, there's only so much we can do. We're one small institute, but we try to do an awful lot by having everybody believe that that's an important part of our culture. On our website, we have, stories that are meant to be understandable, and, we try as best we can to do that. I've taught a MOOC. Actually, somebody who came here told me they took my MOOC. Somebody out there has taken my MOOC. One of these, an online course on Introduction to Biology. And that has been a really interesting experience. When MOOCs first began around 2004, 2005 or so, I did the first MOOC at MIT on biology, this intro bio course. And I gotta say, the number of people I hear from, some 40,000 people a year sign up to take it in some form or another. They don't all complete it. But I'll just tell you one of many, 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 many stories that happen. I was having dinner in my neighborhood at this little Italian restaurant that has 3 tables one summer night. And I'm sitting there trying to do some work because my family's away. And this guy is staring at me from the other table, like all through this dinner. And finally, he screws up the courage to come over and say, "Are you Eric Lander?" And it turns out he was an Iraqi refugee who went to Turkey and couldn't get a work permit in Turkey, but he could take MOOCs. And he took my MOOC and was now working at the Harvard Medical School as a lab assistant. And I've come to realize from emails and other things that the things we do, the ripples we send out there, whether it's, BUR sending out its ripples or whether the MOOCs and the teachings and the lectures we do, they touch lives. And so I've gotten notes like this from Indonesia and from all over the place, from someone in Princeton, New Jersey, who was in the late stage of a neurodegenerative disease and took the course with a pencil, using a pencil in his mouth. The things we do, I think that's the amazing thing is when we do anything, we don't know what the ripples will be on other people's lives. And I've been lucky enough through that MOOC and some of the emails I get back to just be reminded that every act we make has these consequences, and if we choose to, more for good than bad.
And it's like you're reaching out in a way, whether you can see the person or not. It's about starting a conversation. You mentioned how important it is to listen and not just instruct. And in a way, it's like, you can have almost just this, abstract conversation where you're learning from one another. And that's pretty amazing stuff. So last couple of questions here. What practical results of genomic research should we look forward to in the next few years? And as we mentioned before, will they apply to many people or just a few?
I'll give you an example. There's this genetic analysis of common diseases that I was referring to. It's become possible just in the last year to be building predictive scores of your relative risk of different diseases.
Yeah.
So, for example, these polygenic risk scores.
Yes, I actually covered one of these on obesity risk, as a matter of fact, with Dr. Saker Katharaysan. Yeah.
Exactly. And before that, Sake and others at the Broad had this paper on heart disease and breast cancer. So for heart disease, something like 8 or 9% of the population, we can say has a genetic risk that's 3-fold higher for heart disease.
Mm-hmm.
Well, would it matter to know that? Yeah, very possibly. It might be the case you should start on cholesterol-lowering drugs earlier. It might be other interventions should happen. It might be you should exercise more. Exercise is a very good thing. Breast cancer. We know there are these relatively rare genes that put you at risk for breast cancer, BRCA1 and BRCA2 for early onset breast cancer. But now it's clear also that if maybe 3% of the population carries polygenic risk, that's 3-fold higher for breast cancer. So all of these things could ripple out into the medical system in the next few years because it's not that hard to do. Once you have not the whole sequence of your genome, but just genotyping, which not that the medical system will do it at this price, but in fact costs about $20 to do. You can then compute polygenic risk scores for every disease. Now the medical system has to say, well, how am I going to use that? I'm not going to use it for diseases where I don't have a treatment, right? I mean, do you really want to know your polygenic risk score for Alzheimer's? No, because I don't have a treatment for you. I want to know it for medical research, because if we're going to start a clinical trial for a new drug, I'd like to enroll people who are at higher risk but pre-symptomatic, because I can run a smaller trial and therefore more trials. So there are all of these different uses I can make. I think we're going to begin to see, going back to this theme of big data, these biology and data being used in this way in the medical system. And the medical system have to do an awful lot of adjusting to figure this out because most people weren't trained how to use it because nobody knows how to use it.
Absolutely. All right, last question.
Last question already? Oh my goodness!
I know, right? Honestly, like
we could go to Otto's afterwards and just keep going.
Why not? Yeah, just all of us will all pack in.
Yeah.
Why should people get their genome sequenced now? To advance the science, advance the medicine, to advance personalized care, or a combination of all of them? So science, medicine, personalized care, all of the above. What should take?
So I haven't got my genome sequenced. Let's start there.
I think I read that.
Yeah, because I want to emphasize that I don't want to overpromise that if you got your genome sequence, it's going to transform your life, right? The medical system has to catch up in a lot of ways to be able to do this. If, God forbid, I had cancer, I would have the tumor and my normal genome sequenced in a heartbeat because I'd want to know what the mutations were, because there are actionable choices I could make about those drugs. If I had a disease and I wanted to contribute to medical research, I would give my genome, or give a sample so that people could sequence my genome, but I'm not sure I want to know my genome. Right now, I'm at the age where I don't think I have a lot of big genetic surprises to come, and so I want to advance science, and therefore I want zillions of people to voluntarily choose to advance science. We've started something the Broad called Count Me In, which is a program where cancer patients anywhere in the United States can sign up to be part of Count Me In, and they can provide a saliva sample for their genome. They can give us permission to get the medical records, to get the tumors, and thousands of patients have done this across a number of cancers, and really remarkable discoveries have come in some cases. We're not returning the genomes to them right now. They are part of the movement to try to accelerate progress against the disease, and we're not promising them this is going to affect your treatment. Mm-hmm. We're promising them this is going to advance progress against cancer. So I want to be really careful not to say you should all go race out and get your genome sequenced because it's going to improve your life. There are a lot of things that can improve your life, and I wouldn't put this like on the highest thing. On the other hand, if you have an opportunity to contribute to medical research without this information from lots of people voluntarily doing it, we're not going to make progress. So I want to, again, I just go back to my thing of I don't want to overpromise. I think what I can promise is this kind of knowledge is transformative because it's teaching us about the basis of all these diseases. It's giving us the cellular pathways. It's giving people the idea of where they can target drugs, and it's a public common good. Don't think about it as what it's going to do for your health yet. And what it will do for your health is as those drugs get made, they're going to be usable. Over time, with these polygenic risk scores and all that, you may indeed want to get that information. It's the first thing that's made me think I might want my genome in my medical record. Because if already, maybe made by age, I don't care so much, but for many people where it might be actionable to find out, you might want to do it. So I could imagine in 5 or 10 years, I might tell you all you should get your genome sequenced because the medical system has enough that they'll do with that information, which maybe brings me back to, sort of where to end, which is I try not to have didactic opinions about this. For a while, I've said, I don't get my genome sequenced. I don't really see why you'd get your genome sequenced. I'm willing to change my mind in the face of data. I'm beginning to see data and opportunities that might make us act differently. I think that's why we have to have these kind of conversations between scientists and non-scientists across the whole society, so we have the understanding and the trust to navigate through a world that is going to continue to change. This world of science, of genetic knowledge, of the opportunities that will come from it, is going to change tremendously over time. And the answers aren't in the back of the book. We're going to have to work them out together. So, thank you.
Scientist through and through. Dr. Eric Lander, everybody. Thank you all so much for coming out. That was a blast. And just once again, thank you for coming out and making this night at Boston Brilliance amazing. And we don't have any events scheduled just yet, but we will. So I want all of you to come back because they will be just as fun as this one, I hope. So anyway, thank you all very much for coming tonight.
Thank you.
He meant a lot to him and the Red Sox community.
I don't know if here they said, but back home, they talk about superheroes without capes. And he's a superhero without cape. That's the way we see him.